The group of unsaturated hydrocarbons with the general formula CnH2n-2 is known as alkynes. Alkynes contain at least one triple bond between two carbon atoms. The first of the alkyne series is ethine, with the chemical formula C2H2. Ethine, also known as acetylene, is used for arc welding in combination with oxygen gas, which is known as oxyacetylene flame. Alkynes have less number of hydrogen atoms than that of alkanes and alkenes. Hence, though their names are different, the nomenclature of alkynes is invariably dependent on the corresponding alkane. In the IUPAC system, alkynes are named by replacing the ANE of the corresponding alkanes by the suffix YNE. For example, ethane becomes ethyne and propane becomes propyne. In a structure, the carbon atom with the triple bond is assigned the lowest number. This lowest possible number of the carbon atom also denotes the position of the triple bond. However, in some alkynes, there may be more than one possible structure because the position of the triple bond may be different in each structure. For example, pentyne has two structures, as shown here. In one structure, the position of the triple bond is 1, whereas in the other, it is 2. They are named as pent-1-ine and pent-2-ine. When two compounds differ in their structures due to the position of their triple bond, they are known as position isomers. Let's see if we can arrange the atoms in a different way to get another different structure. You can see that we got a chain structure of the same compound. Such a structure is known as a chain isomer. In this structure, the position of the triple bond is 1. Therefore, the name of the isomer will be 3-methyl-but-1-ine. Now let's understand the structure of ethine molecule in relation to a triple bond. An ethine molecule has two hydrogen atoms bonded to two carbon atoms. Each carbon atom has two sp hybridized orbitals and two unhybridized p orbitals. The head-on overlapping of the two sp hybridized orbitals of the two carbon atoms forms a carbon-carbon sigma bond. The sp hybridized orbital of each carbon atom overlaps with the 1s orbital of each hydrogen atoms along the internuclear axis. This overlapping forms two carbon-hydrogen sigma bonds. The hydrogen-carbon-carbon bond angle is 180 degrees. The unhybridized p orbitals in each carbon atom lie perpendicular to each other as well as to the plane of the CC sigma bond. The two p orbitals undergo lateral or sideways overlapping, forming two pi bonds between the two carbon atoms. Hence, an ethine molecule consists of one carbon-carbon sigma bond, two carbon-hydrogen sigma bonds, and two carbon-carbon pi bonds. The electron cloud between two carbon atoms is cylindrically symmetrical about the internuclear axis. Therefore, the shape of ethine molecule is linear. The carbon-carbon triple bond is shorter than carbon-carbon double or single bond. As the triple bond is shorter, it is stronger compared to single and double bonds. First, let's look at the industrial preparation of ethyne from calcium carbide. In this method, initially limestone is subjected to thermal decomposition, in which it results in the formation of quicklime. Quicklime obtained is heated to high temperatures with coke to get calcium carbide. When this calcium carbide is subjected to hydrolysis, ethyne or acetylene is formed. Alkynes can also be prepared from vicinal dihalides, that is, 1,2-dihaloalkanes. A vicinal dihalide molecule has two halogen atoms, each linked to two adjacent carbon atoms. When treated with alcoholic potash, the molecule undergoes dehydrohalogenation. In dehydrohalogenation, first, an atom of halogen on one carbon and an atom of hydrogen present on adjacent carbon in the alkyl dihalide are eliminated as one molecule of hydrogen halide. This results in the formation of alkenyl halide. This alkenyl halide, when treated with a strong base such as sodamide, another molecule of hydrogen halide is eliminated, thus resulting in the formation of an alkyne. For example, when 1,2-dichloroethane is treated with alcoholic potassium hydroxide, forms vinyl chloride, and this, when treated with sodamide, forms ethyne. Do you know why a strong base like sodamide is required for the formation of ethyne from vinyl chloride? As the chlorine atom is directly attached to double-bonded carbon atom in vinyl chloride, it is made highly unreactive. In other words, as the non-bonding electrons of chlorine and the pi electrons of carbon-carbon double bond are in conjugation, the carbon-halogen bond acquires a partial double bond character and the removal of it becomes difficult. Hence, a strong base, such as sodamide, is required for the removal of hydrogen chloride from vinyl chloride to form ethyne. Alkynes follow the same physical characteristics of their predecessors, alkanes and alkenes. The first three alkynes of the series are gases. The alkynes from the 4th to the 11th in the series are liquids, while the higher ones in the series are solids. All alkynes are colorless and odorless, except ethyne, which has a characteristic smell. The CH bond attached to carbon atom with triple bond in alkynes. Alkynes exhibit some polarity, unlike alkenes and alkenes, which are non-polar. This is because the CH bond in alkynes is slightly polar due to the sp hybridization of carbon. As alkynes are non-polar and water is polar, alkynes are water insoluble. However, they dissolve in non-polar organic solvents like ethers, carbon tetrachloride, and benzene. The melting point, boiling point, and density of alkynes are directly proportional to their molecular masses. Coming to their chemical properties. Alkynes exhibit more acidic behavior than alkenes and alkanes. For example, sodium metal reacts with ethine, forming monosodium ethanide and disodium ethanide. Similarly, propene with one hydrogen atom attached to triple bond carbon atom on reaction with soda amide forms sodium propanide. Sodium metal and sodamide are strong bases and do not react with alkanes or alkenes, as they are not acidic. This shows that alkynes are more acidic in nature than alkanes and alkenes. Let's understand why. The hydrogen atoms in ethine are attached to the sp hybridized carbon atoms. On the other hand, the hydrogen atoms in ethene and ethane are attached to the sp2 and sp3 hybridized carbon atoms, respectively. The sp hybridized orbitals of carbon atoms in ethine molecules have 50% of s character and hence the highest electronegativity. These electronegative orbitals attract the shared electron pair of the carbon-hydrogen bond towards the carbon of ethine to a greater extent than the sp2 and sp3 hybridized orbitals of carbon in ethene and ethane. Therefore, the hydrogen atoms in ethine can be liberated easily as protons. This makes the hydrogen atoms of ethine, which are attached to the triply bonded carbon atom, acidic in nature. The addition reactions in alkynes are electrophilic in nature due to the availability of loosely held pi electrons. As alkynes contain a triple bond, during an addition reaction, they add two molecules of dihydrogen, halogen or hydrogen halides to form a saturated molecule. Vinylic cation is formed as an intermediate during the addition reaction of an alkyne. Whereas alkyl carbocation is formed as an intermediate during the addition reaction of an alkene. As vinylic cation is less stable than alkyl carbocation, alkynes are less reactive towards the addition reactions than alkenes. Hence, the addition reactions of alkynes takes place under drastic conditions when compared to the addition reactions of alkenes. Let's go through some addition reactions of alkynes. An alkyne reacts with two molecules of dihydrogen in the presence of suitable catalysts like finely divided nickel, platinum or palladium to form the corresponding alkane. For example, propyne reacts with two molecules of dihydrogen in the presence of finely divided nickel as catalyst to form propane. Alkynes form dihaloalkene when treated with one molecule of halogen and form tetrahaloalkane when treated with two molecules of halogen. For example, when ethine reacts with one molecule of bromine, it forms 1,2-dibromoethene. And when it reacts with two molecules of bromine, 1,1,2,2 tetrabromoethane is formed. The reddish-brown color of bromine decolorizes due to the formation of saturated 1,1,2,2-tetrabromoethane. Thus, this reaction is used as a test for unsaturation. Alkyne, when treated with 2 molecules of hydrogen halide, forms gem dihalide. On the other hand, when treated with 1 molecule of hydrogen halide, it forms alkenyl halide. Addition in unsymmetrical alkynes takes place in accordance with Markovnikov's rule. This rule says that in an electrophilic addition reaction, the negative part of an addendum attaches itself to the unsaturated carbon atom of the molecule having lesser number of hydrogen atoms. For example, propyne reacts with 2 molecules of hydrogen bromide and forms 2,2-dibromopropane in accordance with Markovnikov's rule as shown here. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. However, in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius, alkynes add 1 water molecule to give aldehydes or ketones. For example, ethyne reacts with a water molecule in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius to give ethanol. Similarly, propyne reacts to give propanone. Polymerization is of 2 types: linear polymerization and cyclic polymerization. When heated in the presence of a catalyst, alkynes undergo polymerization. In linear polymerization, the alkyne molecules form a long chain polymer. For example, linear polymerization of ethyne produces polyacetylene or polyethine. Polyethine is a high molecular weight polyene which consists of repeating units as shown here. The polyethine molecule is represented as shown. It conducts electricity under special conditions. This is why a thin film of polyethine is used as an electrode in batteries. In cyclic polymerization, alkyne molecules add to each other, resulting in the formation of a cyclic compound. For example, when ethyne is passed through a red-hot iron tube at 873 Kelvin, it undergoes cyclic polymerization. In this cyclic polymerization, 3 molecules of ethyne polymerize to form benzene. Because of their polymerization abilities, alkynes combine to form many different compounds. For example, benzene obtained by the polymerization of acetylene is used for the preparation of dyes, drugs, and a large number of other organic compounds. Aromatic hydrocarbons are so named as they possess a pleasant smell. Hydrocarbons containing conjugated cyclic rings are called aromatic hydrocarbons. These aromatic hydrocarbons are also called arenes. Aromatic hydrocarbons can be further classified as benzenoids and non-benzenoids on the basis of the presence or absence of benzene ring. Aromatic hydrocarbons containing isolated or one or more fused benzene rings are known as benzenoid aromatic hydrocarbons. Benzene is the parent compound in benzenoids. It is an aromatic hydrocarbon with 6 carbon-hydrogen bonds arranged in a hexagon. Examples of aromatic hydrocarbons containing fused benzene rings are naphthalene, anthracene, and so on. Certain other aromatic hydrocarbons such as azulene and tropolone, which do not contain benzene ring, are known as non-benzenoids. All 6 hydrogen atoms in benzene are equivalent. Therefore, replacing a hydrogen atom with an alkyl group yields only one type of monosubstituted product. Thus, the monosubstituted products of benzene do not show isomerism. However, when 2 hydrogen atoms of a benzene ring are replaced with 2 similar or different alkyl groups, there is a possibility of formation of 3 isomers. These differ in the position of the alkyl group. Thus, disubstituted product of benzene show position isomerism. The 3 position isomers of a disubstituted benzene are ortho, 1, 2 or 1, 6. Meta, 1, 3 or 1, 5. And para, 1, 4. Thus, the 3 position isomers of dimethylbenzene or xylene are 1,2-dimethylbenzene or orthoxylene, 1,3-dimethylbenzene or metaxylene, and 1,4-dimethylbenzene or paraxylene. Benzene, with the molecular formula C6H6, was first isolated by Michael Faraday in 1825. Due to its characteristic properties and unusual stability, the determination of the actual structure of benzene took many years. The following key facts were taken into consideration to determine the structure that we have today. The ratio of carbon to hydrogen in benzene is the same. That is, 1:1, which is evident from its molecular formula C6H6. This fact tells us that it is a highly unsaturated compound. When benzene is treated with ozone, it forms triozonide. The formation of triozonide indicates that it has 3 double bonds. Further, it produces only one monosubstituted derivative, which indicates that all its 6 carbon and hydrogen atoms are equivalent. On the basis of these facts, in 1865, Friedrich August Kekulé gave the first insight into the structure of benzene. He proposed a structure in which the 6 carbon atoms were arranged to form a hexagonal ring with each carbon atom carrying 1 hydrogen atom. The structure had alternate single and double bonds. The structure of benzene suggested by Kekulé is now known as the Kekulé's structure. However, Kekulé's structure could not explain all the properties of benzene. For example, this structure cannot explain the observed bond length of carbon-carbon bonds, which is 139 picometers. According to this structure, 2 bond lengths are expected due to the presence of alternate single and double bonds. They are 154 picometers due to carbon-carbon single bonds and 133 picometers due to carbon-carbon double bonds. This structure cannot explain the formation of only one 1,2-disubstituted benzene, because, according to this structure, two isomeric 1,2-disubstituted benzenes should result. For example, as shown here, in isomer 1, the two chlorine atoms are attached to carbon-carbon single bond, whereas in isomer 2, the two chlorine atoms are attached to carbon-carbon double bond. Hence, there is a possibility of two isomeric 1,2-dichlorobenzenes. However, experimentally only one 1,2-dichlorobenzene product is obtained. To explain this, Kekulé proposed two interchangeable isomeric structures for benzene. These structures are obtained by interchanging the positions of the double bonds, which happens due to the delocalization of the pi electrons between the 6 carbon atoms in the benzene ring. However, Kekulé's structures alone do not explain the unusual stability and the characteristic substitution reactions of benzene. This peculiar behavior of benzene is explained by considering the concept of resonance in Kekulé's structures. We have already learnt that if a molecule that can be represented by two or more structures, and these structures differ only in the arrangement of electrons, then the molecule is said to be in resonance, and the set of several possible structures are called resonance structures, or canonical structures, or canonical forms. Any two resonating structures are represented by inserting a double-headed arrow between them. These are the resonance structures or canonical structures of benzene. The actual structure of benzene is a hybrid of these two resonance structures. It is called a resonance hybrid. This resonance hybrid is more stable than any of the contributing resonating structures. The resonance hybrid is represented by inserting a circle or a dotted circle in the middle of the hexagonal ring of benzene. The dotted circle in benzene represents the delocalization of the pi electrons between the carbon atoms. The difference between the energy of any one of the equivalent contributing structure and the energy of the resonance hybrid is known as resonance energy. The resonance energy of benzene is found to be 36 kilocalories per mole. Due to this, the resonance hybrid of benzene is more stable than any one of its equivalent structures. The resonance hybrid explains most of the properties of benzene. Benzene undergoes substitution in preference to addition due to resonance. If benzene undergoes addition reactions, it loses its stability as the product formed is not resonance stabilized and hence is less stable. On the other hand, if benzene undergoes substitution reactions, the resonance stabilized benzene ring is preserved in the product too. Therefore, benzene undergoes substitution reactions. The resonance hybrid of benzene explains the observed bond length. As it is evident from the resonance hybrid of benzene, due to the continuous delocalization of the pi electrons between the carbon atoms, all carbon-carbon bonds are equal, and the carbon-carbon bond length in benzene is intermediate between carbon-carbon single bond and carbon-carbon double bond. Hence, the bond length in benzene is 139 picometers. As all the carbon-carbon bonds are equivalent, it results in the formation of only one 1,2-disubstituted product. In order to understand the structure of benzene in a better manner, let's look at its orbital structure. According to the orbital structure, each carbon atom in benzene undergoes sp2 hybridization. One unhybridized p orbital remains on each carbon atom. Among the three sp2 hybrid orbitals, two sp2 hybrid orbitals of each carbon atom overlap axially with the sp2 hybrid orbitals of the neighboring carbon atoms, forming 6 carbon-carbon sigma bonds. The third sp2 hybridized orbital of each carbon atom overlaps with the 1s orbital of a hydrogen atom, resulting in 6 CH sigma bonds. Thus, all the carbon and hydrogen atoms in benzene lie in the same plane with the bond angle of 120 degrees. Here, each carbon atom is left with one unhybridized 2p orbital at right angle to the hexagon of the carbon atoms in benzene. We know that the p orbital has two equal lobes, one lying above the other below the plane of the ring. These unhybridized 2p orbitals of the carbon atoms overlap each other sideways, as shown here. As there is equal probability of p orbital of each carbon atom to overlap with adjacent p orbitals of carbon atoms, it results in the formation of two continuous donut-shaped pi electron clouds, one lying above and the other below the plane of the carbon atoms. This delocalized pi electron cloud makes the benzene more stable than the hypothetical cyclohexatriene. Hence, this is the resonance hybrid of benzene. We know that the stabilization of benzene takes place due to resonance, which is also responsible for its aromatic character. In 1931, Erich Huckel proposed the modern theory of aromaticity, or aromatic character of compounds. The property of a cyclic polene or cyclic ion with alternate double bonds and delocalized pi electrons to undergo substitution reaction in preference to addition reaction is called aromaticity or aromatic character. Cyclic rings or heterocyclic rings or cyclic ions are said to be aromatic if they show the essential properties such as complete delocalization of the pi electrons, planarity, and presence of 4n plus 2 pi electrons in the ring. Let's discuss each in detail. Let us look at the first essential property that is required. The molecule should contain a cyclic cloud of delocalized pi electrons. For delocalization of pi electrons, the ring must be planar to allow cyclic overlap of the p orbital. Therefore, for a molecule to be aromatic, the ring must be planar. Now, let us look at another essential property. For aromaticity, a cyclic compound must contain a total of 4n plus 2 pi electrons, where n is an integer, which can be equal to 0, 1, 2, 3, and so on. This means, for a compound to show aromaticity, it must be planar or cyclic, and it should have delocalized 4n plus 2 pi electrons. This is known as the Huckel's rule. Thus, according to Huckel's rule, the aromatic compounds should have a delocalized electron cloud of pi electrons, such as 2, 6, 10, 14 electrons. The example of aromatic compounds are benzene with 6 pi electrons, naphthalene with 10 pi electrons, and anthracene with 14 pi electrons. When N is equal to 1, 2, 3, respectively. Benzene was first isolated by Michael Faraday. In 1845, August Wilhelm Hofmann and his team isolated benzene from coal tar. Commercially, benzene is isolated from coal tar by subjecting it to fractional distillation. However, we can also prepare benzene in the laboratory by several methods. Cyclic polymerization of ethyne, decarboxylation of aromatic acids, reduction of phenol. Let's look at the cyclic polymerization method. Benzene was first synthesized by Marcellin Berthold by passing ethyne through a red-hot iron tube at 873 Kelvin. In a laboratory, benzene can also be obtained by the decarboxylation of aromatic acids. Sodium benzoate, on heating with a decarboxylating agent, that is, soda lime, loses carbon dioxide and forms benzene. Benzene can be prepared by the reduction of phenol by passing its vapors over heated zinc dust. Next, let's learn about the physical properties of benzene. Benzene is a colorless liquid with a characteristic smell. The boiling point of benzene is 80 degrees Celsius. Due to its non-polar nature, benzene is insoluble in water, but soluble in organic solvents such as alcohol and ether. Benzene is highly inflammable. It burns with a sooty flame due to its high carbon-to-hydrogen ratio. Thus, in general, aromatic compounds that produce sooty flames are distinguished from aliphatic compounds that produce non-sooty flames. If we take a closer look at the orbital structure of benzene, we find that the cyclic, delocalized pi electron cloud is loosely held above and below the plane of the benzene ring. The resonance stabilization of benzene is due to the delocalization of these pi electrons. This structural arrangement makes the loosely held pi electrons available for electrophiles, the electron-seeking reagents. Thus, the substitution reactions in benzene are electrophilic in nature. Hence, we can conclude that benzene undergoes typical electrophilic substitution reactions due to the retention of resonance stabilization of the ring, that is, aromaticity. Some common electrophilic substitution reactions of benzene are halogenation, nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation, and sulfonation reaction. Before we proceed into the detailed study of each type of reaction, let us have a look at the mechanism of a general electrophilic substitution reaction. A general electrophilic substitution reaction involves 3 steps. They are generation of the electrophile, formation of carbocation, a sigma complex intermediate, and removal of proton from the carbocation sigma complex. Now, let's take a closer look at each type of electrophilic substitution reaction along with the mechanism in detail. First, let us take up halogenation reaction. The replacement of a hydrogen atom by a halogen atom such as fluorine, chlorine, bromine, and iodine in a benzene ring is called halogenation of benzene. Let us discuss chlorination and bromination, which occur at a temperature between 310 and 320 Kelvin. Usually, the halogenation takes place in the presence of a Lewis acid such as anhydrous aluminium chloride or ferric chloride or ferric bromide, as they help in the generation of electrophile, that is, halonium ion. When benzene is treated with chlorine in the presence of anhydrous aluminium chloride, it results in the formation of chlorobenzene. Let us discuss the mechanism of this reaction. First, an electrophile, that is, chloronium ion in this case, is generated when anhydrous aluminium chloride combines with the attacking reagent chlorine, as shown here. In the second step, chloronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. The sigma complex, which is stabilized by resonance, is shown here. Note that the second step is always a slow step or a rate-determining step, as the aromaticity is lost with the formation of sigma complex. This is because in the sigma complex, one of the carbon is sp3 hybridized and the delocalization of electrons is not possible. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of chlorobenzene. Note that the last step of the reaction is always a fast step, as the non-aromatic sigma complex is converted to aromatic compound. Now let us look at nitration. When a hydrogen atom in the benzene ring is replaced by a nitro group, it is known as nitration. Nitration is carried out by heating benzene at about 330 Kelvin with the nitrating mixture consisting of concentrated nitric acid and concentrated sulfuric acid. When benzene is treated with nitrating mixture, it results in the formation of nitrobenzene. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the nitronium ion here, is generated when sulfuric acid transfers a proton to nitric acid, as shown in these reactions. The reaction between sulfuric acid and nitric acid is an acid-base reaction in which relatively stronger acid, sulfuric acid, acts as an acid, whereas nitric acid, which is relatively a weaker acid, acts as a base. In the second step, nitronium ion attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile HSO4- ion. This results in the formation of nitrobenzene. Now let's look at Friedel-Crafts alkylation reaction. When the hydrogen atom in a benzene ring is replaced by the alkyl group, it is known as alkylation reaction. When benzene is treated with alkyl halide in the presence of anhydrous aluminium chloride, it forms alkyl benzene. This reaction is known as the Friedel-Crafts alkylation. For example, when benzene is treated with methyl chloride in the presence of anhydrous aluminium chloride, it results in the formation of methyl benzene or toluene. Similarly, benzene reacts with ethyl chloride in the presence of anhydrous aluminium chloride to form ethyl benzene. Let's discuss the mechanism of this reaction. First, an electrophile, which is a carbocation here, is generated when anhydrous aluminium chloride combines with the attacking reagent ethyl chloride, as shown here. In the second step, the carbocation attacks the pi electron cloud of benzene ring and forms the less stable intermediate called sigma complex or arenium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of the nucleophile Cl- ion. This results in the formation of ethyl benzene. It is important to note that in Friedel-Crafts alkylation reaction, when benzene reacts with N-propyl chloride, isopropyl benzene instead of N-propyl benzene is formed. This is due to the fact that the less stable primary carbocation formed in this step rearranges to a more stable secondary carbocation. Hence, is the result. Now let's look at the acylation reaction. When the hydrogen atom in a benzene ring is replaced by the alkyl group, it is known as acylation reaction. When benzene is treated with acyl halide or acid anhydride in the presence of anhydrous aluminium chloride, benzene forms acyl benzene. This reaction is called the Friedel-Crafts acylation. For example, when benzene is treated with acetyl chloride in the presence of anhydrous aluminium chloride, it forms acetophenone and hydrochloric acid. Let's discuss the mechanism of this reaction. First, an electrophile, that is, the alkyl ion here, is generated when anhydrous aluminium chloride combines with the attacking reagent acetyl chloride, as shown here. In the second step, alkyl ion attacks the pi electron cloud of the benzene ring and forms the less stable intermediate called sigma complex or aranium ion. In the last step, the proton is removed from the intermediate sigma complex in the presence of nucleophile AlCl4- ion. This results in the formation of acetophenone. Similarly, benzene reacts with acetic anhydride in the presence of anhydrous aluminium chloride and forms acetophenone and acetic acid. Next is sulfonation reaction. When the hydrogen atom in a benzene ring is replaced by the sulfonic acid SO3H group, it is known as sulfonation. Usually, sulfonation reaction is carried out by heating benzene with fuming sulfuric acid or oleum, a concentrated solution of sulfur trioxide in sulfuric acid. Sulfonation can also be carried out by treating benzene with chlorosulfonic acid. Note that during electrophilic substitution reactions, if an excess of electrophilic reagent is used, then further substitution reaction may occur in which the other hydrogen atoms of benzene may also be successively replaced by the electrophile. For example, benzene, on treatment with an excess of chlorine in the presence of anhydrous aluminium chloride in the dark, gives hexachlorobenzene. Let's move on to the next type of chemical reaction, addition reaction. Addition reactions occur under drastic conditions at high temperature and pressure. For example, benzene reacts with hydrogen in the presence of a catalyst such as nickel or platinum at 473 to 573 Kelvin under pressure to form cyclohexane. Benzene reacts with chlorine or bromine in the presence of ultraviolet light to form benzene hexachloride or BHC. BHC is used as an insecticide and sold under the names of gamma-axane or lindane or 666. Next, let's discuss the oxidation or combustion reaction of benzene. Usually, aromatic hydrocarbons are stable and not readily oxidized. Hence, on heating in the presence of air or oxygen, benzene burns to produce carbon dioxide and water along with a sooty flame. The presence of higher carbon content than the hydrogen content in benzene produces the sooty flame. Moreover, this sooty flame test is used as an identification test to distinguish aromatic from aliphatic compounds. As we know, benzene undergoes typical electrophilic substitution reactions and forms monosubstituted benzene as the product. When this monosubstituted benzene is subjected to further electrophilic substitution, it forms 3 possible disubstituted products in varying amounts. The disubstituted product formed in major amounts depends on the reactivity of the monosubstituted benzene. In turn, the reactivity of the monosubstituted benzene depends on the nature of the group that is present on the ring. A group can be either electron-releasing or electron-withdrawing. The group present on the ring orients the new incoming electrophile to any of the remaining 5 positions. Of these 5 remaining positions, with respect to position 1, position 2 and 6 are equivalent and said to be the ortho positions. Positions 3 and 5 are equivalent and said to be the meta positions, and the position 4 is said to be the para position. The position that the incoming electrophile will occupy depends upon the availability of electron density in the ring, which in turn again depends on the nature of the group G already present in the benzene ring. This is known as the directive influence of a group. This influence could either be ring activating or ring deactivating. Ring activating groups are plus R groups or electron releasing groups which make the electron density relatively rich at ortho and para positions of the ring. Hence, these groups orient the new incoming electrophile to ortho and para positions. Ring deactivating groups are minus R groups or electron withdrawing groups which relatively decrease the electron density at ortho and para positions of the ring. In other words, the electron density is relatively high at meta position. Hence, these groups orient the new incoming electrophile to meta position. For example, the hydroxyl group in phenol, due to the minus inductive effect, withdraws the electron from the ring. Hence, ideally, the electron density at ortho and para positions should relatively decrease. But it is found that the electron density at ortho and para positions is relatively more. This is because of the plus resonance effect, which overweighs the minus inductive effect. Thus, the reactivity is predominantly controlled by the plus resonance effect of hydroxyl group. Due to the plus resonance effect of hydroxyl group, the ring gets activated and the incoming electrophile is directed to the ortho and para positions. The following resonance structures of phenol show that the electron density is much concentrated at ortho and para positions than that at the meta position. Thus, ring activating groups are said to form ortho and para substituted compounds in major amounts. Other ring activating groups include NH2, NHR, NHCOCH3, OCH3. Ortho and para directing groups facilitate electrophilic substitution by increasing electron density on the benzene ring and are called ring activating groups. On the other hand, the nitro group in nitrobenzene, due to the minus resonance effect, withdraws the electrons towards itself. Thus, the electron density in the ring decreases. Due to the minus resonance effect of nitro group, it becomes difficult for the ring to undergo further electrophilic substitution reactions. Therefore, the ring is said to get deactivated. In the presence of the nitro group, the electron density at meta position is comparatively higher than the electron density at other positions, and thus the incoming electrophile is directed to the meta position. The following resonance structures of nitrobenzene shows that the electron density is less concentrated at ortho and para positions than that at the meta position. Thus, the incoming electrophile is directed to the meta position. Thus, ring deactivating groups are said to form meta-substituted compounds. Other ring deactivating groups include CN, CHO, COR, COOH, COOR, and SO3H. Thus, we see that the type of group present on the benzene ring influences further substitution reactions in it.